Alrighty, this one is for all of you that are still struggling just a bit with Lewis dot structures and polarity, nonpolar, and even VSEPR models. So this is just a review and wrap up of what we have been learning for the past 2 weeks. So let's just kind of get started here. This first slide that I have will come in handy because not only will it serve as our periodic table, but it'll also show us the electronegativities along the way. If you need this, just make sure that you're going back to my bonding 4, I believe it was called under modules, that you have the entire PowerPoint there for your perusal when you need it. Okay, so we'll be coming back to here every once in a while just so that I can have the periodic table. So the first thing we started off with was just drawing some simple Lewis dot structures for just simple elements. So I'm just going to do maybe 2 or 3 of these just to review a little bit. So the first thing you want to do with these Lewis structures is first put down the element symbol, which is aluminum, and then go back to the periodic table to find out which group it's under. If you recall, this would have been our 1 plus, 2 plus. I'm just going to fill these in a bit so we're going to be dealing with oxidation numbers later on. 4 can either be plus or minus. That kind of depends. Then 3 minus, 2 minus, and 1 minus. Okay, so we find aluminum here in group 13, which we can also call 3. 1, 2, 3. So that means it has 3 electrons in its outermost shell. So let's go back over here and we just simply put our dots going around accordingly. If you start counterclockwise, continue counterclockwise. If you go clockwise, continue clockwise. It doesn't really matter. Okay, fluorine. If we head over here again, we notice that fluorine is found over here. Where's my fluorine? There it is. Over here in group 7. Okay, so that means it has 7 valence electrons. So let's fill them in. Okay, so these aren't too bad. Neon's going to follow suit. If you were to look on the periodic table, it's going to have 8 valence electrons. It's under the noble gases. They're considered inert because they have a complete octet going around it. It's happy. Okay, a boron ion. This is an ion, which means we're going to have something like this here, remember? It would have had 3 around it originally, but this is an ion, and it's going to give away 3 electrons. As a result, I just got this new bamboo pen, so it's taking a little bit of time to get used to it. Okay, so it had 3, and we're going to take those away because we have an ion. So let me just remove all this to make it look better. Alrighty. Since it got rid of its 3 electrons, it forms a 3 plus. So back here, when I did this 3 plus over here, that's because it got rid of 3 electrons when it's getting ready to bond with something, and it's left as a 3 plus as a result. And notice here's boron. Okay, so that is the boron ion. It does not have any electrons anymore because it got rid of them, and it's ready to bond with something that is a nonmetal. Okay, let's go over here for this last one, for a bromine ion. It had 7. This time it wants to gain that extra electron, so I'm just going to put it down here. And as a result, it's a 1 minus. So if you look over here, once again, I had this as a 1 minus. It accepts 1 more electron right there. Okay, so that's how to do a simple Lewis dot structure. Here are the rules one more time to help you out. So you determine the total number of valence electrons first of all, and then you're going to form bonds between the atoms. Recall that you want to put the less electronegative element in the center, with the exception of hydrogen, and that's because I know that hydrogen is less electronegative than carbon, but the problem is you can't stick hydrogen in the center because there's only 2 bonding sites. When you're dealing with just pure compounds like this, and you're not dealing with ions, you can just write who's contributing what. We know that carbon contributes 4, so I'm going to put 4 around it. I know that hydrogen gives 1, so I'm going to have hydrogen give its 1. Okay, once I see two dots, I like to make them into lines to show me that there are some real bonds going on here. And then we should have, first of all, did 4 times 2 plus 6 times 1 to count up how many electrons we needed. So we have 8 and 6, which is 14 electrons. Let's go and count, make sure we have 14 electrons. This one bond here contributes to 2, so we have 2, 4, 6, 8, 10, 12, 14. Good. Hydrogen follows the duet rule, that they're all happy. Carbon follows the octet rule, so they are happy. So this looks like a good structure. Okay, so you can just keep doing that as you're going along. I'm going to do one more here just because this one is going to get a little bit tricky. We have to move these around a bit. So let's look here at C2H4. First thing, we have 8 plus 4 electrons, so we have 12 electrons altogether. Once again, we're going to put our C's side by side. That's already 2 right there. Okay, I have 4 hydrogens this time, so hydrogen's going to give 1. Okay, I'm going to just make these into bonds so I don't have to look at all these dots. Okay, so let's count and see how many electrons we have. 2, 4, 6, 8, 10, 12, 13. 2, 4, 6, 8. No, I'm sorry. 2, 4, 6, 8, 10, 11, 12. Good. So we have 12 electrons placed, but notice how we only have 2, 4, 6 going around this carbon plus that one here is 7. That's just 1 electron. And then we have 2, 4, 6 plus this one here, which is 7. Well, carbon's not getting the octet that it desires. So what we're going to do is take these 2 little loner electrons, and we're going to scooch them here in the center and form a double bond. So let's get rid of those. And we're going to go back and put that into the center. So this one gave its electron put in the center, and this one gave its electron and put in the center. Now let's count and make sure that we have octet, duets, and enough electrons placed. So 2, 4, 6, 8 carbon. Good. 2, 4, 6, 8 carbon here. 2 around hydrogen, 2 here, 2 here. This is good. Okay, so you have to keep practicing these. You're not going to be perfect at these right away, so just keep on practicing them, making sure that you are looking at all of these rules as you're going along. Now, just as a brief reminder, if you're seeing any type of charges, that means you're either going to add electrons or subtract electrons, depending if you are positive or negative. Since we have OH minus, it's going to be adding an electron. So we have 6, because oxygen's in group 6, then hydrogen is 1, 1, and then we add 1 electron. So, what do you say, so I'll get used to this new pen, plus 1, and then we have 1 more electron. So we have 8 electrons that we need to place. Okay, so we have oxygen, which is at 6, and then we have hydrogen already. We need 8, I'm going to put another one here. Don't forget, whenever you are doing these, you need to put the charge out there signifying that you have an ion. Let's make sure that we have 8s and that everything is following either the octet or duet rule. 2, 4, 6, 8 around oxygen, 2 around hydrogen. That's the right structure. So just keep on working these. If you have any individual problems, then come and see me. I'm going to move on now. After we did those, we started to look at Vesper, which were the different molecular shapes with the bond angles associated with each one. So starting off here at the linear, we have the 2 bonds, and notice how they're in a straight line and they form a 180-degree angle. Okay, then we moved on to, let's just say, a structure that had 1 in the center and 3 true bonds going around it. 3 true bonds, no lone pairs, just 3 bonds. So that's called the trigonal planar, sometimes trigonal planar, and it has a 120-degree angle on it. Then we went into 4 bonding sites. If we have 4 true bonds with no lone pairs, then we call it a tetrahedral, and it has a 109.5-degree bond angle. Now, if we had a parent structure that was tetrahedral, but we had 1 lone pair, much like this one right here, we have 1 lone pair and 3 true bonds, then those little lone pairs cause 2.5 degrees of repulsion. Okay, so that means we take this parent structure, which is 109.5, and subtract 2.5 2.5 to get 107 degrees. So if you are looking at 3 true bonds with 1 lone pair, then we call that a trigonal pyramidal. Okay? And the last one that we have to deal with are these bent molecules. That means that it has two true bonds, and then it has 2 lone pairs. So we have 2 true bonds, and then we have 1 lone pair and 2 lone pairs. Recall that I said earlier that each lone pair causes 2.5 degrees of repulsion. 2.5 plus 2 times 2 is 5. So we're going to subtract 5 here. So it'll give us 104.5, but we just round this up to 105 degrees. Okay? So 105 degrees on this one. Alrighty. So again, you're going to have to, we did a little lab with these where we did some ball and stick little structures to put these together. You're going to have to make your Lewis structures and then determine which one of these 5 that you have. Okay, so this is here for you if you need it. And we'll just do maybe one of these real quick. Let's do BF3, this first one that we see. There were 3 of them, and then we have 21, so we have 24 electrons that we need to place. Boron is the less electronegative of the 2, obviously, because fluorine is the most electronegative element on the periodic table. Okay, let's go here. 24. Okay, well, we have already 6 placed. 2, 4, 6. Let's go around for fluorine. 6, and then we have 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, now this one is fine. Okay, boron sometimes does this. It doesn't have to follow an octet. It's one of those exceptions to the rule. Okay, so this one, since it has 3 true bonding sites, if you recall, this was called the trigonal planar with bond angles of 120 degrees. Okay, so you're going to keep doing the same thing. Once again, make sure you count up your electrons, place them correctly, determine how many true bonds you have, how many lone pairs. Find your actual structure over here, and then make sure that you not only name it properly, but that you are also saying the bond length. Okay, and these are just going to give you some more practice. I would highly recommend, even if you finish them, just going back over these and doing a few more, just so that you definitely have a good understanding of these. We can maybe do one of these together right now if you'd like. Let's do the PO4 3-. If, let's see, whoops, let me get my thing here. If you look at the P, it's over 5, then we have 6 times 4, and then we added 3 electrons, so we have 24, 29, 32 electrons that we have to place, okay? So let's go and look. Once again, we put our P in the center. And I'm just going to place these electrons. Since we're dealing with these charges, we don't really know who's giving what. So just go ahead. I always start here in the center and put these in at least. There's 8. And then I'm just going to keep on going until I stop at 32. So here we go. We have 8, 10, 12, 14, 16, 18, 20. 22, 24, 26, 28, 30, 32. Check. Okay, everything has 8 going around it. Don't forget to put this in brackets and show its charge, letting your audience members know that you added 3 random electrons somewhere so that they know where those came from. Okay, so always count up those electrons, place them, make sure that they're following either the octet or duet rule, and then if they're not, make sure you're shuffling around these electrons so that everything is happy. And then we would, if we wanted to take this one step further, we have 4 true bonding sites going around this phosphorus, so that was a tetrahedral. 4 true bonds at 109.5. No degrees of repulsion because I don't have any lone pairs. Notice how there is a true bond here, true bond here, true bond here, true bond here. There's nothing that just has a little lone pair. So that would be the right structure there. So go ahead and keep doing these. They're good practice. The last thing that we looked at was polarity. Okay, if we want to look at your electronegativities, and if you're wondering where those are, just come on back here to this very first slide. You're going to do some subtraction. Just make sure whoever is the highest goes first. So, you know, you might have like something like NO that you're trying to figure out. Just do the higher of the two first. So we have 3.5 minus 3.0. So you have 0.5 right there. Okay, so that's the electronegativity difference between those particular elements. So let's go back over here and review the rules that you need. If you're dealing with these polarities, you want to make sure that you're understanding the difference between electronegativities. If it is under 0.5, it's going to be a nonpolar molecule. Okay, if it's at 0.5 to about 1.7, you're going to have what's called a polar covalent bond. It's still covalent. You're still going to have two nonmetals together, but it's going to be in that polar covalent range. So you have to do these electronegativity differences. If it's sitting at 0.5, well, it can be a little bit iffy, so the best thing that you want to do is actually draw out the Lewis structure. If you draw out the Lewis structure and notice two or more lines of symmetry, then you're dealing with a nonpolar bond. So when it's sitting right at 0.5, the best course of action was just to make sure that you are doing the Lewis structure for those. So that's just what this is kind of saying right here. If they're under 0.5, less than 0.5, it's going to be nonpolar. Okay, and then we had a few other things that we were dealing with from there, and I gave you those rules later on. Like it could either be what we have polar bonds in between, or hydrogen bonds, or even these van der Waals forces. The van der Waals forces are only going to be found in nonpolar bonds, so you don't have to worry about those, unless of course the electronegativities are under 0.5. So once again here, I gave you the information. So what you were supposed to do is just kind of go over these and look through them to see which one of these up here would work out with these here. Okay, and I gave you some notes in class that you can look back over your notes to make sure that you understand the difference between which one is the hydrogen bonding and which one are just the polar covalent bonding. And they had to do with what it was being bonded with. If hydrogen was being bonded with nitrogen, oxygen, or fluorine, then it's going to come together and make a hydrogen bond. And if you have hydrogen bonding that is not with nitrogen, oxygen, or fluorine, then you just have a typical polar bond. If you're getting electronegativities greater than 1.8, 1.8 or greater, then you're dealing with ionic bonds. And usually with ionic bonds, if you recall, you have to have a metal with a nonmetal. Okay, so these are metals plus a nonmetal. Whereas the rest that I just talked about, all of this, are the two nonmetals together. Okay, they all form some sort of covalent bond. We have to figure out if it's polar or nonpolar. If it is polar, again, under polar, we could have polar bonds, or we could have hydrogen bonding. And it all depends on if hydrogen is being bonded with nitrogen, oxygen, or fluorine. Okay, so I hope that this helped a little bit with your understanding. Watch this video as many times as you need to get comfortable with the information. If you are still struggling or having any problems, please come and visit me for tutoring after school on Thursdays. I'm up in the STEM space. And let me know, okay? This is pretty simple information if you just keep practicing it, but don't let it snowball and get out in front of you. All right, I hope this helped, and I'll see you guys in class.